Ninth webinar of the MSS webinar series brought to you by IEEE Malabar subsection in association with IEEE Student Branch IIT Palakkad. When you're looking at a photo that just looks a little bit too perfect or a little bit beyond the range of normal, an object or even a landscape that's in uncanny valley, there's a chance you're not looking at a photo at all. You could be looking at a hyper-realistic 3D design. The magic of 3D graphics is the ability to push images beyond the realistic and onto a new magical plane. And to dwell more into the world of 3D graphics, we have with us a very special guest, an individual with many brilliant accolades to his name. Mr. Abhishek Rhisheekesan is the founder and MD at aiRender Technology Private Limited, a startup working towards the next leap in video conferencing. He has also worked as an engineering manager at graphics architecture labs at Intel, leading a highly prolific team of 20 engineers. He holds an MS degree in computer science from Arizona State University and was the recipient of the Outstanding Graduate MS Student Award. He holds 3 US patents in 3D graphics architecture and several publications. He is a man of distinct vision who has been at the forefront in transforming and inspiring future innovators with his work and spirited contributions. It is my absolute honor and privilege to invite Mr. Abhishek Rhisheekesan to lead today's session on fundamentals of 3D graphics.
Thank you, Dr. Sabik and Dina, for the introduction and providing me with the opportunity to present 3D graphics, the fundamentals of 3D graphics and related topics to the IEEE Malabar Chapter. Good evening, everyone. I think I would like to thank Dina again for providing with a really nice introduction for me. And okay, before we start, so currently I'm the founder and CEO of aiRender, and we are building a 3D video conferencing product. aiRender is part of the startup incubation program, Venture Devils at Arizona State University in the US. And here is our website and working video conferencing web app link. Please sign up for the video conferencing web app and give it a try. Here's the agenda for today. Let me get to the topics. Okay. Our universe exists in multiple dimensions, possibly more than 10. An average human being can perceive the world around him or her in 3-dimensional space. Most existing computer applications visualize the space in 2 dimensions. In the last century, with the introduction of computer-generated graphics, many applications have started visualizing the world in 3 dimensions. Today, we are going to take a walk through the world of 3D graphics. Have you ever wondered how 3D games like Counter-Strike, Pokemon, Fortnite, and City Racing work? How do popular 3D software like AutoCAD, Maya, or Unity bring 3D objects, models, and 3D world into action? A 3D game or a 3D world scene can be considered like a movie, which is arranged as a deck of frames or images and played in sequence. Each frame is constructed by converting a world modeled in 3D to a 2D image, a process known as rendering, which we'll talk about in a short while. As an illustration, let's take a look at the rotating cube on the left side. Rendering basically converts the view of the cube from a particular angle and projects it in 2 dimensions onto the computer screen, as shown on the right side. In this section, we are going to get introduced to 3D coordinate geometry, which is basically a foundation of 3D computer graphics. Let's take a look at a simple 3D example at your home. Here is a typical dining table. As you can see, the shape of the dining table is made out of multiple rectangles. For one of the rectangles shown in the previous slide, as part of the dining table, let's now define the coordinates. The rectangle has a length of, let's say, 2 units and width of 1 unit. The rectangle can be split into 2 triangles. One of the triangles has the following coordinates in XYZ coordinate space: 0, 0, 0, 0, 1, 0, and 2, 0, 0. And similarly, all the coordinates of the table can be defined. Now, in this section, we will introduce you to different spaces and the concept of transformations in 3D graphics. Primarily, there are 5 major spaces and 4 main transformations in 3D graphics. First of all, there is a local space which deals with creation of local objects. Then comes world space, which positions multiple objects in a 3D scene. Then we have the view space, which sees the world from a viewer's or a camera's point of view. And further on, there is clip space, which clips the portion of the objects to be shown on the screen and adds perspective projection. Finally, there is screen space, which maps normalized clip space coordinates to a pixel on the screen. For example, a 800 cross 600 screen. Now, let's touch upon the first 2 spaces and the transformation between them. Think of local space as the 3D coordinate space in which a single object is created. For example, the tabletop in the example we showed in the last section is a local object in the shape of a cuboid and can be defined with its own 3D space with its XYZ axis and origin. Now, similarly, a table with the tabletop and its 4 legs and an almirah adjacent to that can be considered to be part of a world space in a specific 3D scene, where they're defined within a common global 3D space with a common origin and XYZ axis. The model matrix, which transforms the local object from its individual local spaces to a common world space, consists of transformations like scaling, translation, and rotation of vertices of these local objects. Now, let's see what a 3D transformation looks like. A 3D transformation is essentially a matrix to vector multiplication. The transformation matrix is a 4x4 matrix, as you can see on the left side here. The vector contains a 3D attribute of a vertex of an object, for example, XYZ geometric coordinates. And the vector is a 4-dimensional vector is 4-dimensional and can be considered as a 4x1 matrix for all practical purposes. The 3D transformation performs a dot product matrix vector multiplication of the 4x4 transformation matrix with the 4x1 3D attribute vector to obtain a 4x1 transform matrix. And the same transformation is generally applied to all vertices of an object. The model matrix mentioned in the last slide performs a translation, rotation, or scaling, or a combination of these for all vertices of an object in a local space to transform it into the global world space. Now, the objects in the world space can be viewed from different angles. For example, we can place the camera on front, top, bottom, or sides, or at specific angles. Here, you can see the top view of the 2 objects after transformation to the view space. View space is typically called as eye space or camera space. Viewing the exterior through a window can best explain the transformation from view space to clip space. This is similar to placing the objects in view space into the rectangular window of the world visible through a computer monitor. Some objects like the boundary wall in the picture shown here gets clipped. Some of the plants which falls within the boundary of the viewing window is included within the clip space and are shown completely, while some of the other objects like the gate and the kennel on the left and right sides of the viewing window respectively get discarded. Okay, screen space converts clip space objects to pixels on the screen. The screen may be of the resolution 1920 cross 1080 pixels for a laptop, for example, or 480 cross 900 pixels for a mobile phone. Now we are going to view orthographic and perspective projections and the corresponding frustums in this section. To understand orthographic projection, let's consider Bombay-Pune Expressway and viewing it from a helicopter or a drone. For most part, one of its lanes appears like two parallel lines at both sides of the road for a straight stretch of the road. This is an orthographic view of the road. Typically, orthographic projections are done for faraway objects. The orthographic frustum view shows near plane and far plane parallel to each other, as shown on the right here. And most importantly, similar sized in terms of what can be viewed within it. Think of near plane as a computer monitor and far plane as the plane including the farthest object you can see within the scene, and parallel to the computer monitor's screen or the near plane. The planes are near and far with respect to the viewer's eye or camera position. The space between the near plane and far plane is called a viewing box. The viewing box of orthographic projection is a cube-like frustum box. As you can see, the objects which fall completely within the viewing box, like the green cube over here, is completely visible and included in the view. The red cube which falls outside the view box is discarded, and the blue cube which falls on the boundary of the viewing box is clipped. Now, here is the perspective projection of the same lane from Bombay-Pune Expressway. If you stand on the lane and view the far stretch of the straight road as far as you can view, the two edges of the road seem to merge towards the far stretch as shown here. The distance between the edges seem to be wider towards you and seem to be closer towards the far end of the road. This is a typical example of perspective projection and takes real life perspective of the scene. If you are gone to a drawing competition for small kids, you can see most of the pictures, be it for roads or houses, are drawn as orthographic projections. Most of the engineering drawings are orthographic projections, whereas the great paintings of Da Vinci or Raja Ravi Verma capture perspective projection. Farther objects in orthographic projections seem to be the same size as nearer objects, and that creates a weird view of the scene. Now, let's stand in awe of the simplicity of the frustum view of the perspective projection. Again, the laptop screen can be considered as the near plane, and the plane containing the farthest object in the scene can be taken as the far plane. The length and height of the far plane seems larger than the near plane. The four sides joining far plane and near plane are trapezoidal in shape. Here again, the objects within the view box or clip space volume, as it is called, like the blue cube, are captured in the view completely. The ones on the boundary, like the red cube, are clipped, and the green cube outside the frustum view is discarded. Now, there are three parameters that define a camera's viewing direction. Imagine a fighter plane. Consider the XYZ axis of the plane as shown in the figure. The rotation about the y-axis and in the XY plane, XZ plane, is called yaw. as shown here, and the rotation about the x-axis and in the YC plane is known as pitch. And finally, the rotation about the z-axis and the xy plane is known as roll. The rotations can be in clockwise or anti-clockwise directions. Similarly, a camera can be rotated along these axes and positioned for a particular view of the scene with specific yaw, pitch, and roll parameters. Now, in this section, we are going to take a deep dive into depth. To understand depth, consider a chair that's behind a trolley bag or a paper on top of a chair. The portion of the chair that's behind the paper or behind the trolley bag will not be visible and hence doesn't need to be rendered. The structure as we call the buffer we use to record the depth of different objects to check which object is in front of the other object is called depth buffer. The depth buffer has values ranging from 0.0 to 1.0 for all pixels on the computer screen. 0.0 represents the near plane corresponding to the objects that are closest to the camera, and 1.0 represents the far plane, which relates to the objects that are farthest in the scene from the eye view. So an object X, which is in front of an object Y, will have a smaller value of depth versus Y in the range 0.0 to 1.0. Before you receive any objects to render, all values in the depth buffer are initialized to 1, setting them as farthest in the scene. Now, in the previous section on Introduction to Coordinate Geometry, objects are shown to be built from multiple triangles. Depth corresponds to z coordinates of vertices of triangles. Let's consider a triangle from the upper left half of the chair as shown here. Imagine a rectangle covering that triangle with its sides parallel to the length and breadth of the computer screen. For sake of simplicity, assume all vertices of the triangle have a depth value of 0.8 corresponding to their z coordinates. So this triangle passes the depth testing, and the corresponding locations in the depth buffer as shown on the right are marked as 0.8. These locations map to the imaginary rectangle covering the triangle. Depth test pass means the chair triangle will continue through further steps of rendering. Now comes a triangle from the trolley bag towards its bottom, which doesn't overlap with any portion of the chair. So this triangle also passes depth testing, similar to the previous one, and the respective locations in the depth buffer are marked with its depth value of 0.5 and 0.5. Now, let's consider a triangle from the chair that overlaps with the trolley bag towards the middle of the scene as shown. And since this triangle is one to reach depth testing first, it passes depth test, and mapping locations in depth buffer are marked as 0.8 as shown here on the right. And here comes a triangle from the trolley bag, which overlaps with the previous triangle from the chair towards the middle of the scene. Note that the depth of the trolley triangle is 0.5 and less than the 0.8 depth of the chair triangle. So it passes the depth test, and mapping locations in the depth buffer are overwritten with its depth value of 0.5. Now, on the other hand, assume the same trolley triangle came for depth testing before the middle scene chair triangle. It passes depth test, and the depth buffer locations are marked as 0.5. Now, since the chair triangle came for depth testing after the overlapping trolley triangle, it fails depth test as its depth is 0.8 and higher than the trolley triangle's 0.5. The chair triangle essentially is discarded from further rendering. In this section, we will play with stencils, as in the stencil used by many of you when you were kids. Stencil is pretty much same as the stationary stencil that most of you had used in your schools. Typically, it's used for showing alphabets and numericals in a 3D graphics scene, and at the same time ensuring that the background 3D graphics scene is rendered without any disruptions. Here are a couple of real-life examples of 3D graphics games that utilize stencil. As you can see on the left bottom corner, the player 1 Lakshman is being shown using stencil. Here are the alphabets in Lakshman are sort of carved out using stencil, and the background 3D graphics scene of the game is visible through the letters, while the box containing the alphabets of Lakshman occlude the background 3D scene. Similarly, stencil is used to showcase options of different guns of the same player, as shown here on the right. Now, stencil testing is implemented using stencil buffer. It's similar to the depth buffer shown in the last class. Stencil values of 0 to 1 are used in stencil buffer to indicate whether or not to render each pixel on the screen based on a stencil mask, which we will shortly introduce in the next slide. All values in the stencil buffer are initialized to 0. Here is a stencil mask which shows the letter L in Lakshman. As you can see, the locations in the stencil buffer mapping to the portion of the 3D graphics game scene visible through the region of alphabet L are marked as 1, indicating its visibility. At the same time, the stencil buffer locations mapping to the brown box covering the stencil mask for letter L are all set to a value of 0, which indicates the mask will be occluding or covering the background region. That's pretty much the world of stencil testing. In this section, we'll see the dark side of backface culling. Now, the most popular face culling method is backface culling. Consider the tabletop that we had seen in the prior sections. If the viewer or the camera is seeing the top view of the tabletop, the top face of the tabletop is visible and the bottom face of the tabletop is not seen by the viewer. The top face and the bottom face of the tabletop are rectangular in shape and are made up of 2 triangles each, as discussed in the previous sections. In order to perform backface culling, we assign a winding order to the vertices of each triangle. From the exterior of the tabletop, vertices of all triangles are numbered incrementally in a counterclockwise direction. The vertices are numbered in counterclockwise direction as if the triangle is facing you. As you can see, the vertices on one of the triangles on the top face of the tabletop are numbered from 1 to 3 in counterclockwise direction. Similarly, the vertices of one of the triangles on the bottom side of the tabletop are numbered from 4 to 6 in the counterclockwise direction if you are viewing it from the bottom side. If you assume that the triangle is facing you, in this case from the bottom side, but when you view from the top, the winding order of the vertices of the bottom face triangle becomes clockwise as shown here. Now all triangles with clockwise winding order are culled and rest of the triangles with counterclockwise winding order are retained and are visible. This is essentially backface culling. Now, this section is going to delve into one of the most important topics in 3D graphics rendering called rasterization. Most of you may be familiar with the raster scanning methods in older television sets. As we have seen in one of the earlier sections, 3D objects are made from polygons, 3D polygons, and 3D polygons are made from triangles. which are the basic building blocks of 3D objects. As you can see here, the tabletop is a rectangle, which is a polygon, and it consists of two triangles. Now, rasterization in a sense involves converting the triangles of 3D objects in the 3D scene into pixels on the computer screen. Now, the basic requirements for rasterizing two adjacent triangles, that is, triangles that share a common edge, involves it should not leave any holes, that is, not non-rasterized pixels between the two adjacent triangles, so that the rasterized area is completely filled. No pixel is rasterized more than once, that is, the rasterized triangles should not overlap. Now, in order to achieve these requirements, certain rasterization rules are established. One set of such rules is top left rule. It states that a pixel is rasterized if and only if its center lies completely inside the triangle, or its center lies exactly on the triangle edge, that is either top or left edge. In case of corners, the pixel center lies exactly on the multiple edges, that is top or left edges. Now, a top edge is an edge that's exactly horizontal and lies above other edges. And a left edge is a non-horizontal edge that is on the left edge of the left side of the triangle. As you can see in the figure, the red edge in the triangle on the left is a left edge, and the red edge in the triangle on the right is a top edge. Now, let's go through a rasterization algorithm. In order to reduce the number of pixels that need to be traversed as part of rasterization for each triangle, the algorithm computes a bounding box for the triangle to be rasterized. Now, computing the bounding box involves finding the minimum and maximum x and y coordinates of the three vertices making up the triangle in raster space. Once you compute the bounding box of the triangle, the next step is to iterate only over the pixels within the bounding box to rasterize the triangle, rather than rasterizing over the entire set of pixels on the computer screen. Rasterization checks whether each pixel in the bounding box is inside or outside the triangle using the rasterization rules we discussed in the prior slide. Now, this section helps you learn how to sample texture maps. First of all, let's see, why do we need texture sampling? Let's take an example of a high quality 3D face like the one shown on the right side. A typical high quality 3D face requires anywhere between 40,000 to 60,000 vertices or more. If we were to color each vertex separately, it requires an RGB color value per vertex amounting to around 40,000 to 60,000 RGB color values. That takes a lot of space in the memory to store the values. Now, instead, let's consider a texture map. Think of texture map as a blanket wrapped over the 3D object. For example, consider the tabletop shown below. We can wrap it up with a texture map of plywood texture as shown here. Typically, texture maps are stored as single image or multiple images. Here, the plywood texture image is shown on the right and has a width of 400 pixels and a height of 200 pixels. And the texture coordinates in the axis along the width or the x-axis are typically called u coordinates, and the ones along the height or the y-axis are called v coordinates. UV coordinates are scaled from 0 to 1, as shown here. Now consider the top facing part of the 3D tabletop object that we discussed in the prior slides. The rectangular tabletop can be split into two triangles, and the XYZ coordinates of the vertices of the triangle are as shown below. Now the vertices of the top right triangle are mapped to UV coordinates in the plywood texture image. For example, the top right corner vertex with XYZ coordinates 210 are mapped to a pixel location with UV coordinates 0.8 and 0.9 in the texture image, and the corresponding RGB value of that pixel is mapped as the color for that vertex. Similarly, other vertices of the triangle can be mapped to different UV coordinates in the texture image as shown here. Now, the advantage with storing such a texture map is that it can be reutilized for texture mapping the same person's face in different scenes in a 3D graphics application. Now, this section will introduce you to the concept of shaders in 3D graphics. Before going into shaders, let's see how a typical 3D graphics pipeline looks like. A 3D graphics application is fed by the game programmer or the graphics application programmer to the 3D graphics pipeline, which is implemented in both software as well as hardware. Different blocks in a 3D pipeline are shown here, and we have already gone through most of these blocks in detail in prior sections like clipping, culling, rasterization, depth, stencil, texture mapping, etc. For now, we will focus on vertex and fragment shader blocks. Each block in the pipeline has a specific function, as you can see, like rasterization or texture mapping, as explained in the prior sections. Now, some of these blocks are programmable and can be customized by the game programmer, like the vertex shader and the fragment shader. Mostly, the vertex locations and pixel colors of each vertex and each pixel are independent of other vertices and pixels, or only dependent on the neighboring vertices or pixels. So, the vertex and fragment shaders are highly parallel for small programming blocks. Now, let's see what's a vertex shader. It primarily performs transformations of XYZ location coordinates or other attributes like normals of vertices of triangles in a 3D object. It performs rotation, translation, scaling, zooming, or other similar transformations of the triangles. The transformations of the triangles and vertices were discussed in one of our prior sections. The diagram here shows the rotation of the vertices of a triangle. Vertex shader takes the 3D XYZ coordinates or other attributes of a single vertex as its input. Similarly, the output of the vertex shader consists of the transformed 3D coordinates or vertex attributes of a single vertex. The primary function of a fragment shader or pixel shader is to determine the final color of a pixel. The input to the pixel shader is the initial color of a single pixel. For example, it can be the color of the nearest vertex to the pixel, or it can be fed with a uniform color for the entire triangle. The input pixel is obtained after rasterization of triangles to pixels and possibly after depth and stencil testing, as shown in the diagram on the right. The output of the pixel shader is the final color of the pixel as shown in the diagram of the rasterized pixels of a triangle on the bottom right. The pixel shader may run lighting algorithms or shadow algorithms, which we can see in detail probably in future sessions. Now, lighting in 3D graphics is a comprehensive topic in itself. If you like this session, we can plan for a session on lighting related topics in the future. Now, here is the YouTube link for the 3D graphics tutorials and the topics that we covered in today's talk. Please do check it out. Thank you all. Now we can open the floor for questions from the audience.
If any of the participants have any questions that you would like to ask our speaker, please put it in the chat box or you can unmute your mic and speak. Okay, so there's a question that just came in through the private chat asking about your experience in your startup and how you actually got into the world of 3D graphics.
Okay. While I was working with my prior company, Intel, in many of the video conferencing meetings that I held with the counterparts, my counterparts in other geographies, for example, from US and other locations, I felt a general lack of trust. And once you travel there and meet these same counterparts, there is a phenomenal buildup of trust. So basically that translates to like the face-to-face meetings. There are a lot of visual social cues that you can capture in a sense, like your body language, facial expressions, gestures, etc., which convey a lot of the information. In fact, according to many research studies, it's more than 50% of the information that you convey over a conversation is through these facial expressions, body language, and just hand gestures and all. So that basically prompted me to come up with something that is better than 2D video conferencing, and at the same time doesn't require you to travel all the time and meet your counterparts across geographies or in remote locations or anything. And that's where I got the idea of 3D, coming up with something like a 3D video conferencing in thin air, which is probably the next best thing to meeting somebody in person. So we are trying to build a 3D video conferencing solution, as in like you can see the participants in the room as walking 3D projections in a live streaming mode in thin air. So basically, currently the software part of it's ready, and we are working on the hardware part of it, which involves a holographic projector. Hope that answers the question.
Thank you, sir. Another question that came in was like, if there was something that is unattainable right now with regards to 3D graphics, but you would like to do so in the future, what would it be?
Could you please repeat the question?
If there are some challenges with regards to accomplishing something in with regards to 3D right now, because you do not have the sufficient technology or it has not been yet developed, but you would like to see in the future, what would it be?
I think, yeah, I mean, as we are working on a 3D video conferencing, right, with high resolution and accessible to masses, right? That's one of the things that's lacking in today's world. We have academic solutions for 2D to 3D reconstruction of audio, of still images as well as video clips and all. But there are niche solutions for converting 2D videos to 3D videos for certain specific applications. For example, the talk that Honorable Prime Minister Narendra Modi gave during his campaigns in 2014 and 19, were projected using a holographic projection device to 200 locations, where the audience could see the 3D projection of the Prime Minister in thin air. But that was used for that specific application and is kind of extremely expensive solution. We want to bring that to the masses. So that's one of the areas I think that I could comment upon. But otherwise, I guess some of the companies like Facebook, Microsoft, and all, Apple, and all are working on metaverse sort of solutions, which could basically revolutionize the future working spaces as well as personal interaction space, which would be built in 3D basically. Hope that answers the question.
Thank you, sir. We have a question from Shaza. What would be the system requirements to meet 3D video conferencing?
We are building So like I was mentioning, we built a 3D video conferencing software solution already. This involves capturing the videos of meeting participants using usual 2D cameras that you see in your laptop or mobile phone or AR/VR headsets for that matter. They capture the 2D video streams. These are converted to 3D corresponding 3D video streams using machine learning. And once you get the 3D video streams, these are, using usual video conferencing sort of solution. There are multiple open source frameworks for that. You can transmit the 3D video streams to all the participants. And finally, it's rendered. Initially, our idea is to render it in like AR/VR headset sort of environment or 3D TVs. This is typically done using game engines like Unreal Game Engine and Unity and all that. And eventually, we want to project it into thin air using holographic projectors. Now, holographic projectors work on the concept of diffraction, which many of you would have learned in your, in the physics sessions in your school. And it basically works on the interference pattern that's created. And it basically works on something like what you call the smooth horizontal parallax projections. So it gives a feel of the depth, and that could be seen in thin air because of the diffraction patterns created. The hardware basically would involve, there are multiple ways to do that. There is something called anisotropic leaky mode modulator based systems, and there are something called spatial light modulators, or some of the semiconductor companies also come with something called digital micro mirror devices. So you can use some of these devices to create the diffraction pattern and come up with the holographic projection in thin air. Hope that answers the question.
Thank you so much, sir, for answering all our questions and for the very engaging session. On behalf of IEEE Malabar subsection and IEEE student branch of IIT Palakkad, I would like to extend our deepest gratitude, sir, to you for providing us with a multi-dimensional perspective about 3D graphics. We are deeply indebted to you, sir, for taking a significant portion of your time amidst your very busy schedule to join us here. Thank you so much, sir.
Thanks a lot, Dr. Sabik and Dina, for organizing this session, and thanks a lot to the engaging audience, and the pleasure was all mine.
Thank you, sir. Thank you. Thank you.
We have come to the conclusion of our webinar on the fundamentals of 3D graphics. I hope you have been inspired by the unparalleled learning, thought-provoking, and insightful pointers this session has given. I would like to thank everyone that have been involved in the organization of this program for their dynamic efforts, and all the honorable dignitaries who have graced this occasion with your esteemed presence. Thank you to all of you here for spiritedly participating and joining us regularly for the MSS webinar series. Please note that a feedback link has been posted in the comment section. Do go through and fill it up. Thank you once again, all of you. You may now leave the meeting room.